In mathematics, a recurrence relation is an equation that recursively defines a sequence or multidimensional array of values. Once one or more initial terms are given, each further term of the sequence or array is defined as a function of the preceding terms. The term difference equation sometimes refers to a specific type of recurrence relation. However, difference equation is frequently used to refer to any recurrence relation. Examples: Logistic map. An example of a recurrence relation is the logistic map. With a given constant r, given the initial term x0, each subsequent term is determined by this relation. Some simply defined recurrence relations can have very complex behaviors, and they are a part of the field of mathematics known as nonlinear analysis. Solving a recurrence relation means obtaining a closed-form solution, a non-recursive function of n Fibonacci numbers. The Fibonacci numbers are the archetype of a linear, homogeneous recurrence relation with constant coefficients. They are defined using the linear recurrence relation with seed values. Explicitly, recurrence yields the equations, etc. We obtain the sequence of Fibonacci numbers, which begins 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89. It can be solved by methods described below, yielding the closed-form expression, which involves powers of the two roots of the characteristic polynomial t2 equals t plus 1. The generating function of the sequence is the rational function. Binomial coefficients. A simple example of a multidimensional recurrence relation is given by the binomial coefficients, which count the number of ways of selecting k out of a set of n elements. They can be computed by the recurrence relation with the base cases. Using this formula to compute the values of all binomial coefficients generates an infinite array called Pascal's triangle. The same values can also be computed directly by a different formula that is not a recurrence, but that requires multiplication and not just addition to compute. Structure: linear homogeneous recurrence relations with constant coefficients. In order, D linear homogeneous recurrence relation with constant coefficients is an equation of the form where the D coefficients Ci are constants. More precisely, this is an infinite list of simultaneous linear equations, one for each n greater than d-1. A sequence that satisfies a relation of this form is called a linear recurrent sequence, or LRS. There are d degrees of freedom for LRS, i.e., the initial values can be taken to be any values, but then the linear recurrence determines the sequence uniquely. The same coefficients yield the characteristic polynomial whose d roots play a crucial role in finding and understanding the sequences satisfying the recurrence. If the roots R1, R2 are all distinct, then the solution to the recurrence takes the form where the coefficients k are determined in order to fit the initial conditions of the recurrence. When the same roots occur multiple times, the terms in this formula corresponding to the second and later occurrences of the same root are multiplied by increasing powers of n. For instance, if the characteristic polynomial can be factored as 3, with the same root r occurring 3 times, then the solution would take the form as well as the Fibonacci numbers. Other sequences generated by linear homogeneous recurrences include the Lucas numbers and Lucas sequences, the Jacob-Stahl numbers, the Pell numbers, and more generally the solutions to Paul's equation. Rational generating function theorem. Linear recursive sequences are precisely the sequences whose generating function is a rational function. The denominator is the polynomial obtained from the auxiliary polynomial by reversing the order of the coefficients, and the numerator is determined by the initial values of the sequence. The simplest cases are periodic sequences, which have sequence and generating function a sum of geometric series. More generally, given the recurrence relation, with generating function a series is annihilated at add and above by the polynomial. That is, multiplying the generating function by the polynomial yields as the coefficient on, which vanishes for nd. Thus, so dividing yields expressing the generating function as a rational function. The denominator is a transform of the auxiliary polynomial. One could also use any multiple of this, but this normalization is chosen both because of the simple relation to the auxiliary polynomial, and so that the generating function of the Catalan numbers is not a rational function. So the theorem tells us that the Catalan numbers do not satisfy a linear recurrence with constant coefficients. Relationship to difference equations narrowly defined given an ordered sequence of real numbers. The first difference is defined as. The second difference is defined as, which can be simplified to, more generally, the kth difference of the sequence, and is written as is defined recursively as. The more restrictive definition of difference equation is an equation composed of an and its kth differences. Actually, it is easily seen that thus, a difference equation can be defined as an equation that involves an, and one, and two, etc. Since difference equations are a very common form of recurrence, some authors use the two terms interchangeably. For example, the difference equation is equivalent to the recurrence relation, thus one can solve many recurrence relations by rephrasing them as difference equations, and then solving the difference equation, analogously to how one solves ordinary differential equations. However, the Ackermann numbers are an example of a recurrence relation that do not map to a difference equation, much less points on the solution to a differential equation. See timescale calculus for a unification of the theory of difference equations with that of differential equations. Summation equations relate to difference equations as integral equations relate to differential equations. From sequences to grids, single variable or one-dimensional recurrence relations are about sequences. Multivariable or n-dimensional recurrence relations are about n-dimensional grids. Functions defined on n-grids can also be studied with partial difference equations. Solving. General methods for order 1. The recurrence has the solution n equals Rn with a0 equals 1, and the most general solution is n equals krn with a0 equals k. The characteristic polynomial equated to 0 is simply t minus r equals 0. Solutions to such recurrence relations of higher order are found by systematic means, often using the fact that n equals Rn is a solution for the recurrence exactly when t equals r is a root of the characteristic polynomial. This can be approached directly or using generating functions or matrices. Consider, for example, a recurrence relation of the form when does it have a solution of the same general form as n equals Rn. Substituting this guess in the recurrence relation, we find that must be true for all n greater than 1. Dividing through by Rn minus 2, we get that all these equations reduce to the same thing, which is the characteristic equation of the recurrence relation. Solve for r to obtain the two roots lambda 1, lambda 2. These roots are known as the characteristic roots or eigenvalues of the characteristic equation. Different solutions are obtained depending on the nature of the roots. If these roots are distinct, we have the general solution, while if they are identical, we have this is the most general solution. The two constants c and d can be chosen, based on two given initial conditions a0 and a1 to produce a specific solution. In the case of complex eigenvalues, the use of complex numbers can be eliminated by rewriting the solution in trigonometric form. In this case we can write the eigenvalues as then it can be shown that can be rewritten as where here e and f are real constants which depend on the initial conditions. Using one may simplify the solution given above as where a1 and a2 are the initial conditions, and in this way there is no need to solve for lambda 1 and lambda 2. In all cases, real distinct eigenvalues, real duplicated eigenvalues, and complex conjugate eigenvalues, the equation is stable, if and only if both eigenvalues are smaller than 1 in absolute value. In this second-order case, this condition on the eigenvalues can be shown to be equivalent to a less than 1 minus b less than 2, which is equivalent to b less than 1 and a less than 1 minus b. The equation in the above example was homogeneous, in that there was no constant term. If one starts with the non-homogeneous recurrence with constant term k, this can be converted into homogeneous form as follows. The steady state is found by setting Bn equals Bn minus 1 equals Bn minus 2 equals B asterisk to obtain. Then the non-homogeneous recurrence can be rewritten in homogeneous forms, which can be solved as above. The stability condition stated above in terms of eigenvalues for the second-order case remains valid for the general nth-order case. The equation is stable if and only if all eigenvalues of the characteristic equation less than 1 in absolute value. Solving via linear algebra, a linearly recursive sequence Y of order n is identical to expanded with n1 identities of kind. This nth-order equation is translated into a system of n first-order linear equations. Observe that the vector can be computed by n applications of the companion matrix C to the initial state vector. Thereby, nth entry of the sort sequence Y is the top component if eigendecomposition into eigenvalues and eigenvectors is used to compute, thanks to the crucial fact that system C time shifts every eigenvector E by simply scaling its components lambda times, that is, time-shifted version of eigenvector E has components lambda times larger. The eigenvector components are powers of lambda, and, thus, recurrent linear homogeneous equation solution is a combination of exponential functions. The components can be determined out of initial conditions. Solving for coefficients. This also works with arbitrary boundary conditions, not necessarily the initial ones. This description is really no different from general method above, however it is more succinct. It also works nicely for situations like where there are several linked recurrences. Solving with Z transforms certain difference equations, in particular, linear constant coefficient difference equations, can be solved using Z transforms. The Z transforms are a class of integral transforms that lead to more convenient algebraic manipulations and more straightforward solutions. There are cases in which obtaining a direct solution would be all but impossible, yet solving the problem via a thoughtfully chosen integral transform is straightforward. Theorem. Given a linear homogeneous recurrence relation with constant coefficients of order d, let P be the characteristic polynomial such that each Ci corresponds to each Ci in the original recurrence relation. Suppose lambda is a root of P having multiplicity R. This is to say that R divides P. The following two properties hold. Each of the R sequences satisfies the recurrence relation. Any sequence satisfying the recurrence relation can be written uniquely as a linear combination of solutions constructed in part 1 as lambda varies over all distinct roots of P. As a result of this theorem, a linear homogeneous recurrence relation with constant coefficients can be solved in the following manner. Find the characteristic polynomial P. Find the roots of P counting multiplicity. Write n as a linear combination of all the roots with unknown coefficients by. This is the general solution to the original recurrence relation. 4. Equate each from part 3 with the known values from the original recurrence relation. However, the values n from the original recurrence relation used do not usually have to be contiguous. Excluding exceptional cases, just d of them are needed. This process will produce a linear system of d equations with d unknowns. Solving these equations for the unknown coefficients of the general solution and plugging these values back into the general solution will produce the particular solution to the original recurrence relation that fits the original recurrence relation's initial conditions. The method for solving linear differential equations is similar to the method above. The intelligent guess for linear differential equations with constant coefficients is E lambda x, where lambda is a complex number that is determined by substituting the guess into the differential equation. This is not a coincidence. Considering the Taylor series of the solution to a linear differential equation, it can be seen that the coefficients of the series are given by the nth derivative of f evaluated at the point A. The differential equation provides a linear difference equation relating these coefficients. This equivalence can be used to quickly solve for the recurrence relationship for the coefficients in the power series solution of a linear differential equation. The rule of thumb is that, and more generally the recurrence relationship for the Taylor series coefficients of the equation, is given by or. This example shows how problems generally solved using the power series solution method taught in normal differential equation classes can be solved in a much easier way. Example: the differential equation has solution. The conversion of the differential equation to a difference equation of the Taylor coefficients is it is easy to see that the nth derivative of EAX evaluated at 0 is in solving non-homogeneous recurrence relations if the recurrence is inhomogeneous. A particular solution can be found by the method of undetermined coefficients, and the solution is the sum of the solution of the homogeneous and the particular solutions. Another method to solve an inhomogeneous recurrence is the method of symbolic differentiation. For example, consider the following recurrence. This is an inhomogeneous recurrence. If we substitute nn plus 1, we obtain the recurrence. Subtracting the original recurrence from this equation yields, or equivalently, this is a homogeneous recurrence, which can be solved by the methods explained above. In general, if a linear recurrence has the form where a constant coefficients and p is the inhomogeneity, then if p is a polynomial with degree r, then this inhomogeneous recurrence can be reduced to a homogeneous recurrence by applying the method of symbolic differencing r times if is the generating function of the inhomogeneity. The generating function of the inhomogeneous recurrence with constant coefficients ci is derived from if p is a rational generating function. A is also 1. The case discussed above, where Pn equals k is a constant, emerges as one example of this formula, with p equals k. Another example, the recurrence with linear inhomogeneity, arises in the definition of the schizophrenic numbers. The solution of homogeneous recurrences is incorporated as p equals 0. Solving first-order non-homogeneous recurrence relations with variable coefficients. Moreover, for the general first-order linear inhomogeneous recurrence relation with variable coefficients, there is also a nice method to solve it. Let then general linear homogeneous recurrence relations. Many linear homogeneous recurrence relations may be solved by means of the generalized hypergeometric series. Special cases of these lead to recurrence relations for the orthogonal polynomials, and many special functions. For example, the solution to is given by the Bessel function, while is solved by the confluent hypergeometric series. Solving a first-order rational difference equation. A first-order rational difference equation has the form. Such an equation can be solved by writing as a nonlinear transformation of another variable which itself evolves linearly. Then standard methods can be used to solve the linear difference equation in stability. Stability of linear higher-order recurrences. The linear recurrence of order D has the characteristic equation the recurrence is stable, meaning that the iterates converge asymptotically to a fixed value, if and only if the eigenvalues, whether real or complex, are all less than unity in absolute value. Stability of linear first-order matrix recurrences. In the first-order matrix difference equation with state vector x and transition matrix A, x converges asymptotically to the steady state vector x asterisk if and only if all eigenvalues of the transition matrix A have an absolute value which is less than 1. Stability of nonlinear first-order recurrences. Consider the nonlinear first-order recurrence. This recurrence is locally stable, meaning that it converges to a fixed point x asterisk from points sufficiently close to x asterisk. If the slope of f in the neighborhood of x asterisk is smaller than unity in absolute value, That is, a nonlinear recurrence could have multiple fixed points, in which case some fixed points may be locally stable and others locally unstable. For continuous f2 adjacent fixed points cannot both be locally stable. A nonlinear recurrence relation could also have a cycle of period k for k greater than 1. Such a cycle is stable, meaning that it attracts a set of initial conditions of positive measure. If the composite function with f appearing k times is locally stable according to the same criterion, where x** is any point on a cycle. In a chaotic recurrence relation, the variable x stays in a bounded region but never converges to a fixed point or an attracting cycle. Any fixed points or cycles of the equation are unstable. See also logistic map, dyadic transformation, and tent map. Relationship to differential equations. When solving an ordinary differential equation numerically, one typically encounters a recurrence relation. For example, when solving the initial value problem with Euler's method and a step size h, one calculates the values by the recurrent. Systems of linear first-order differential equations can be discretized exactly analytically using the methods shown in the discretization article.